Welcome to this Forge College Explainer. Today, we're going to draft the architectural blueprints you need to port your monolithic ERC-20 contract over to Solana's high-speed, separated state model. In our previous lesson, we covered Solana-friendly architectural patterns for porting, so right now, it's time to actually leave all that heavy, expensive EVM baggage behind at the terminal. If you've been working in the Ethereum virtual machine, you're used to one very specific way of thinking about state. Well, today, we're translating that mindset into a concrete, implementation-ready design artifact for Solana. We're going to map out exactly how your ERC-20 flows, things like minting, transferring, and managing allowances, translate into explicit Solana accounts, instructions, and authority flows. So grab your notepad, because we're getting totally hands-on.
Here's the master schematic for today. We'll start with the big porting picture, sketch out our account layouts, map those core flows, tackle the allowance dilemma, verify our design, and finally, make sure we are 100% implementation ready.
All right, let's jump right into Section 1, the big porting picture.
So we are officially moving away from the giant, messy warehouse of Ethereum's global state. Think about it. When you deploy an ERC-20 token on the EVM, you're deploying one massive smart contract that holds a giant mapping of literally everyone's balance. It's kind of like stuffing an entire city's cash into one giant, chaotic warehouse. But on Solana's separated state model, every user and token mint gets their own highly secure, custom-sized safety deposit box. The program, your actual smart contract logic, is entirely separate from the data.
Now, to control these individual safety deposit boxes, we use something called program-derived addresses, or PDAs. A PDA is simply an account whose address is deterministically calculated using predefined program seeds and a bump. Why is this such a big deal? Because it allows our smart contract to act as the undeniable authority over specific accounts. Our program can actually programmatically sign for state changes without needing a private key at all. PDAs are essentially the magic glue holding Solana's separated state together, making absolutely sure that only the right programs can modify the right deposit boxes.
Moving on to Section 2. Sketching the account layouts.
Okay, before we even think about touching any Rust code, we need to define two conceptual schemas in a simple markdown blueprint. First up is the mint account. This holds the global token settings. We need a Boolean for initialization, a public key for the authority, the total supply as an unsigned 64-bit integer, and the decimals. Second, we have the individual holder's token account. This requires its own initialization flag, the owner's public key, and of course, their balance. Separating the global token rules from the individual user balances is just a fundamental, absolutely crucial Solana pattern.
Let's look at the actual math for a standard token account. The exact byte size is 41 bytes. How do we get there? Well, it's 1 byte for the initialization status Boolean, plus 32 bytes for the owner's public key, plus 8 bytes for the unsigned 64-bit integer balance. 1 plus 32 plus 8 equals 41. Simple enough, right?
But knowing this exact footprint isn't just fun trivia. It's a hard structural requirement. Solana requires rent exemption calculations, which means we have to fund exactly the space our blueprint specifies. Whenever you create an account on Solana, you have to lock up a small amount of SOL, proportional to the account's byte size, to keep it alive on the network. If your layout calculations are off even slightly, your account creation will just straight up fail. Dialing in this precision right now makes the coding phase a total breeze later.
Let's hit Section 3, Mapping Core ERC-20 Flows.
This is where the rubber really meets the road. To mint new tokens, we grab the program-owned mint PDA, the recipient's token account, and the rent system variable. We use the mint2 instruction, and it has to be explicitly signed by the mint authority. If that authority is a PDA, it programmatically signs via invoke signed. From there, we just increment the global supply and the recipient's balance. Easy.
Now, for a transfer operation, our instruction is literally just transfer. We need both the sender's token account and the receiver's token account passed in explicitly. And here is the vital part. We need the explicit signature of the sender's owner to actually authorize moving those funds. Once that's verified, the mutations cleanly subtract from the sender's balance and add to the receiver's balance.
I always laugh at this one because it hits the nail right on the head. Wait, who is actually supposed to sign this transaction again? Literally every EVM developer's first day migrating to Solana. In Ethereum, MSG.sender is usually just handled globally and implicitly. If you've ever felt completely lost trying to figure out who authorizes a state change on Ethereum, you are going to love that Solana forces you to be wonderfully, painfully explicit about signer requirements. No more guessing. You map it out in your blueprint, and the security model becomes crystal clear.
Section 4. Solving the allowance dilemma.
So, unlike the EVM, where allowances are just a nested mapping tucked inside the main contract, Solana gives us two primary architectural choices for state placement here. We can either use an inlined approach, which means cramming a bounded vector of allowances directly inside the user's main token account, or we can use a separate PDA approach, generating one distinct, completely isolated PDA for every single owner-spender pair.
Let's weigh these trade-offs real quick. Inlining saves on cross-program calls, since the allowances data is sitting right there in the token account. But it permanently bloats the account size, increasing base rent for every single user, whether they even use allowances or not. On the flip side, using a separate PDA per pair requires more accounts to be passed into your instructions up front, but it makes managing individual allowances so much cleaner. It's essentially pay-as-you-go storage. Your design document must explicitly make this choice and justify it.
Assuming we pick the separate PDA route, we document it. For an approved flow, we pass the owner, the spender, and the brand new allowance PDA to write the allowed amount. For transfer from, we gather the owner's token account, the recipient's account, the spender as a signer, and that specific allowance PDA. The program checks the PDA, decreases the allowance, and moves the funds.
Section 5. Trade-offs and design verification.
As a mental model, a flawless Solana blueprint treats every operation as three orthogonal, independent concerns. Step 1. State placement. Which accounts actually hold the bytes of data? Step 2. Instruction surface. What minimal inputs, accounts, and constraints does the program require to run? And Step 3. Authority flow. Who exactly signs this transaction and when? If your design clearly separates these three things, you are absolutely golden.
Here is your ultimate design verification checklist. Have you mapped all 4 core flows? Are your account layouts sized down to the exact byte integer? Are your signer relationships explicitly named? Have you validated the execution sequence in your head? And did you write down your trade-off recommendations? A reviewer should be able to look at this exact checklist, read your trade-off justifications, and start writing anchor code without having to ask you a single design question.
And finally, Section 6, ready for implementation.
As we wrap up this drafting session, ask yourself one final question. Are your PDA seeds and bump logic clearly defined? Are your rent calculations complete? If you've done the work in your blueprint documents, the answer is a resounding yes. You've mapped the seeds, you know exactly how big the accounts are, and there's simply no ambiguity left.
So what's the crucial takeaway from all this preparation? It's that in the very next step of your journey, you're going to convert these exact schematics directly into anchor-derived macros and instruction handlers, because you already know the fields, the byte sizes, and the exact accounts needed for every single instruction. Filling out the structures in Rust basically becomes automatic.
Remember, mastering this architecture first is your absolute secret weapon. It is what makes writing the Rust code a completely mechanical, stress-free process rather than a frustrating negotiation with the compiler. You aren't guessing about state placement while you're fighting the borrow checker. You're just translating a verified blueprint directly into syntax.
Thank you so much for joining this Forge College Explainer. We've covered a massive mindset shift today, from Ethereum's global mappings to Solana's explicit, high-performance account models. The groundwork you've laid here is going to pay off tenfold when you actually start coding. Be sure to visit forge.college to learn more about porting your projects, accessing our full curriculum, and continuing your transition into the SVM ecosystem. But before you open up your code editor, I want you to ask yourself, if you were to design a protocol that processed 50,000 transactions a second tomorrow, would your state model be a cluttered warehouse or a perfectly tuned matrix of safety deposit boxes? Think about it. See you in the next explainer.